Just setting up the screen. Good morning, everybody. Full screen. Good morning, Matthew. Good morning, Michael, Dilshan, Desiree, Carly. Carly by the fence. Carly's thinking, shall I jump the fence? Is the grass greener on the other side? Hi, Roberto. Hi, Tiana, Jamela, Shannon, Trevin, Lupita, Tiana. Tiana with 2 N's. I'm happy to get a cup of coffee. That's all I need. My needs are very limited, very simple. Simple life and bad thinking, okay? Evil thinking and simple life. I think that's a good combination. How are you guys doing? Come on, say something. Talk to me, please.
How are you doing, doctor?
I'm doing good. That's all I need. See, there is a Massachusetts Bayshore cup, and I like drinking from here. This was a gift from my student who went to dental school. She's going to be my free dentist when I get really old. I'm pretty old, but you know, after maybe 10 years, when I walk with a cane, ride my motorcycle with 2 canes, like motorcycle skating. I'll need like training wheels. All right, no more terrible jokes. 8:01. We lost 1 minute. Very critical. Very, very critical. Okay. Turn my phone off. Anything from anyone? What day is today? Today is Tuesday. Spring break is around the corner. Hi, Judith. Okay, we are recording, and let's go to the board. Let's talk about alkene chemistry. The plan is to talk about alkene chemistry, then get into alkynes, and switch gear. Okay? Hopefully we can finish it. Well, with my track record, it's probably not going to happen. Let's see what can happen here. The camera definitely looks messed up. Hold on for a second. Let me check the video setting. Okay, as usual, the HD is off. Mirror my video. I don't want to mirror my video. Okay, now it's good. I don't know why it does that. All good now. Let me open my window. All right, it's another wonderful day. I think it is a nice day. A little bit of cloud and blue sky and relatively clean air, I believe. M8, and today is February 16. Yeah, not February 16, March 16. March 16. Okay. We're talking about alkene chemistry, alkene reactions. Okay. Let's draw an alkene again. Let's get to the point. This is an alkene. The simplest alkene. There is going to be like a 5-minute review. Okay. And that reacts with, so supposedly that's a pi bond. The pi bond is the lower bond. If you can see the color, that's the blue, that's the red bond, that's pi. Sigma, 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 sigma. 5 sigmas and 1 pi. Okay. And this guy reacts with let's say H something, HF, HCl, HBr, or HI. Okay, one of the 4 halogens. Let's pick HCl. Okay. So the way the reaction works is the pi bond the pi bond, the mechanism, this mechanism is included for your learning. Okay, from the middle of the pi bond, the arrow goes out. That means this bond opens up to the right or opens up to the left and picks up the proton and breaks this bond. And that bonding pair becomes a lone pair now. Okay, I'll just show you in color-coded way as clearly as I can. Okay. I don't know which way I'm going to open the bond. Let's open the bond to the left. And Cl has come out with a negative charge. I'm not showing all the lone pairs. You have to get kind of used to it. Okay. Something is missing. What is missing? What is missing in this molecule? Somebody got the short end of the stick. Somebody lost something and therefore it's not a neutral atom anymore. Who can tell me? Don't use the chat or gestures. Just speak up. What is
The carbon on the right wants to have 4 bonds.
Carbon on the right wants to have 4 bonds. Therefore, it's deprived of what? What is missing? To be a neutral
proton?
bond. It's missing an electron, right? It's supposed to have 4 electrons around itself. Always has 4 electrons. 1, 2, 3, 4. 1, 2, 3, 4. So therefore they're neutral. This guy is having 1 less electron. That means what charge shall I write on it? Craig or anybody? It has 1 extra proton and 1 less electron. That means which charge is excess?
Positive.
I'm not supposed to slow down here, Peyton. Thank you. I'm not supposed to slow down, but make sure you understand that it's this, not that. Because this could be a question. I might put like 3 pictures, 1 neutral, 1 with a positive charge, 1 with a negative charge, and answer D will be none of the above. Which one should you pick? Is this the right answer? Let's say this is answer A. This is answer A, negatively charged. This is answer B. This is answer C, and answer D is none of the above. Negative, neutral, positive, and none of the above. Which one is your pick? A, B, C, D. This is C. Wake up!
It's positive.
Thank you, Daniel. So that's positive, okay? If you're having trouble figuring this out, you need to review the old materials, seriously. Okay, you need to be able to figure out that, well, carbon, here it has 4 electrons in its outermost shell. This guy has 4 electrons in its outermost shell. Hydrogen has 1 electron in its outermost shell. This hydrogen has 1 electron in its outermost shell. The chlorine has 1, 2, 3, 4, 5, 6, 7 electrons in its outermost shell. Right now, this chlorine is having excess electron because it took that electron with it. That's why the bond moved from the middle. Whenever both electrons are moving together, whether right or left, if they're moving together, like both at the same time, then we show that the arrow is starting from the middle of the bond. Okay. So far, so good. So this is called a carbocation. I will spend a little time on it. This is called an intermediate. And it is a carbocation. It's a cation. It's a positively charged species. So cations are positive. anion negative. Okay. This is a special type of carbocation because the positive charge is on a carbon. Therefore, it's a carbocation. Get used to this name. This is important. You guys need to memorize it. It's a carbocation. Okay. We are not done yet. None of the products will remain charged. They will have to be neutralized somehow. How will it get neutralized? Well, it can use, sometimes we show that the negative charge is pushing. That means one of the extra lone pair is pushing. Okay. So I'm just going to show you this way. It's going to, the negative charge is pushing on top of that positive charge. That means it's using one of the one of the lone pairs to make a brand new bond. And so what does it look like after that reaction? And now it's going to use one of those electrons. I don't know whichever one, it doesn't matter. Okay. So now you got an alkyl halide. This is an alkyl halide. We made an alkyl halide. If I just draw it in one color, it'll look like this. It's the same molecule as this molecule is called an alkyl halide. We'll figure out what it's called. When fluorine becomes a branch, let's say you have some alkane. That's the main stem of the tree. When you have a fluorine attached to it, it's called fluoro, F-L-U-R-O. Sorry, F-L-U-O-R-O. When you have a chlorine, it's called fluoro. When you have a bromine, what should I call the bromine branch? If the bromine is staying there as a branch, how shall I call it? Bromine becomes what? Help me.
Bromo?
A little louder.
Bromo?
There you go. Thank you. Bromo. And what about iodine? Somebody else.
Maybe iodo.
Iodo. Sounds good. Okay, great. Thank you. What should we call this molecule? From your knowledge with alkanes and cycloalkanes and alkenes, how should we call this molecule?
Chloroethane.
Who supports and the answer chloroethane? I'm going to write it down. Three out of three, 0 out of 3, 1 out of 3, 2 out of 3, minus 2 out of 3. What do you guys think? Anybody else? Like two answers, 2 supporters or 2 opposition statements. What do you guys think? Chloroethane is a bad idea, good idea?
Sounds good to me.
Michael says that he's with you, Craig. Anybody else? One more. Yay or nay? Come on, wake up.
Looks
What
good to
is
me.
doing? Is that a mannequin like that's sitting in front of your camera, shaking its head like a bubble head? Oh, Dr. Mitra, I don't know. I'm happy. Someday there will be AI robots that can mimic your movements. check out Boston Dynamics. Pretty cool. They actually have a robot dance with 4 robots. It's incredible. I'm not kidding. I don't want to get distracted early in the morning. Okay, chloroethane sounds good. Okay, so this is something you can handle. Everybody in this weird Zoom class, how many of you are there? 29. Okay. I'm going to take a picture of this board and then move to a situation where you can have 2 different carbocations. Okay, let's go. So if you have a symmetric double bond, that's one situation. If you have a dissymmetric double bond, unsymmetric double bond, then the situation gets little sketchy, little dicey situation. Okay, and at that point, 2 things can happen. Two different carbocations can form, and which carbocation is going to be better than the other carbocation? That's going to be our next question. And you need to learn the stability of different carbocations. So that's what we're going to be discussing now. Okay. So now our discussion is going to focus on taking this reaction, alkene reaction with acids, with haloacids or haloacids, not haloacids. Sometimes I get confused about some pronunciations. Some haloacids. So we are basically talking about, we are under alkene. We're talking about reaction with HX, whatever the X is. And then we're going to talk about carbocations. Okay, that's where we are. Okay, now the funny business is we're going to use this double bond. Say this double bond is not symmetric. This double bond is a weird double bond, right? It's got 2 hydrogens on one side and 1 hydrogen and a methyl group on the other side. Take a look at it. So if I draw it this way, it's probably more deceiving. Like you can't really tell what's going on here. Let's show everything in this molecule. Let's show all the body parts. Okay, carbon. I'm not going to expand the methyl group. It's just CH3. Okay, there's a hydrogen here. There's a hydrogen here, and I'm going to draw that double bond pretty much the same way as I drew in the past. Okay, so look at the molecule and appreciate the lack of symmetry in the molecule. It's not symmetrical, right? This molecule will be symmetrical. That's symmetrical. That's symmetrical, right? So they are symmetrical. So left side and the right side, the same things. Okay. So same way, we can call them cis or trans. Okay. This molecule is not symmetrical. Okay, there is no symmetry because left side and right side are different things. These 2 are symmetrical. Okay, now if we do the same reaction on it, what happens? Let's use a different halogen. How about bromine? Let's use bromine now. Same mechanism. The double bond picks up the proton, and the HBr bond breaks and goes on top of the bromine by cutting the bond. The bond gets chopped off here. Okay, sounds good. Now it's not as simple as in the past. All right, let's draw it out. You can actually have, I mean, the main frame of the molecule hasn't changed. Methyl group here, hydrogen here, 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 and here. The bond, the red bond can either open to the right or the red bond can open to the left, right? It's like a gate that's hinged on both sides. I've seen these gates, you know, it's not like rocket science. It's very simple. You unhinge it and you open it to the left, or you unhinge to the left and open it to the right, right? So let's say the first molecule, we open it to the left, and the second molecule, we open it to the right. Okay? And the carbocations, as a result of that, and of course we produce Br minus. Yeah, that's happening anyway. Br minus is happening in this case and in this case. Okay, that's happening. That's on the side because you're splitting the proton from HBr, so it has no other choice but producing Br minus. But the interesting part is this is a cation on a carbon that's attached to two hydrogens. This is a cation, carbocation, that's sitting on a carbon that has only one hydrogen. What does it imply? Which one is better? Okay. Now we're going to discuss carbocation stability. Okay. Carbocations can be a bunch of different ways. You can form carbocations. Let's draw them out. One carbocation can have 3 hydrogens around itself. This is the simplest carbocation. This is one type of carbocation. The second carbocation can have 1 methyl group and 2 hydrogens. That's another type of carbocation. The third carbocation can be 2 methyl groups and a hydrogen. And the fourth carbocation has no hydrogens attached to itself. They're all carbons. You probably learned electronegativity in the past, but you may not have covered it as much as I would have wanted you to. So I'll tell you, how much do you remember electronegativity from general chemistry? Does anybody remember what that is? Can anyone articulate what it means? Let me erase. This is not that important. It doesn't have to be in your picture. It's not so critical. So let me just talk about this property of an element. Electronegativity. Oftentimes it's written as En. What is electronegativity? Anybody remembers? I don't think I have talked much about it in this class, or I might have touched upon it. Does anybody remember what it is?
I remember that that's what pulls the molecule up or down, right?
not really molecule, the bonding electron. So let's say,
Oh yeah, the electrons.
yeah, so let's say you have a carbon-hydrogen bond, okay? Now the question is, we talked about polar bonds. We briefly talked about polar covalent bonds, but I didn't really delve much into it. I was waiting for a moment like this, like an auspicious moment to talk about this business, okay? So this electron is coming from carbon. Okay. And this electron is coming from hydrogen. Now the question is, if I put $10 in a bank account and you put $10 in a bank account, is the bank account, are the $20 going to be equally pulled by you and me, or it's going to be more toward me or more toward you? Okay, so before we can talk about this property of an element, the element must be in a molecule. Okay, so like should the carbon hydrogen bond be equally distributed, or the bond should be more toward carbon and less toward hydrogen, or the bond should be more toward the electron density should be more toward hydrogen and less toward carbon. Okay, so this is electron density. So left side is carbon, right side is hydrogen, right? So it's the power of an element to pull. It's important. The definition is important. I'm going to write it down. It's the power of an element, not by itself, of an element in a molecule. It must be in a molecule. This is very critical. In a molecule, to pull not one electron, but bonding electron, a pair. The pull bonding electron pair toward itself. Read that definition. Electronegativity is the power of an element in a molecule to pull the bonding electron pair toward itself. So if I'm having, can we talk about the electronegativity of the bromine here, Br minus? No, it's not in a molecule. That could be a trick question. Now I'm getting ideas for the next quiz. I hope we're not supposed to have a quiz today. I don't have a quiz. It's the power of an element in a molecule to pull the bonding electron pair toward itself. Okay. Now, as we go from hydrogen, helium, lithium, beryllium, I'm going to work backwards. Neon, fluorine, oxygen, nitrogen, carbon, boron. Okay. Down here we have sodium. Under boron you have aluminum. Under carbon you have silicon. Under nitrogen you have phosphorus. Phosphorus needs a special color. It's not as harmless as that. Sulfur needs a special color. Sulfur, chlorine, bromine, iodine, helium, neon, argon, krypton, Xenon. That's probably good enough. Now, electronegativity, when you're going across a row, okay, you're adding more proton and more electron, right? 1, 1, 2 protons, 2 electrons, 3 protons, 3 electrons, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9, 10, 10, 11, 11, 12, 12, 12 protons, 12 electrons, okay? In the same row, you are not adding a shell, you are just adding more electrons. So as the, what can I say? Let me write it down here. So if this is the nucleus, and these are the shells, shell 1 and shell 2, okay? Let's say you have lithium, okay? In lithium, you have this situation, okay? 3 and 3, 2 in 1s, 1 in 2s. Remember electronic configuration, don't forget about that, okay? As we go from lithium to beryllium, we put one more electron, we put one more electron. As the number of electrons keep increasing in the same shell, then we go to the boron. We put one more proton and we put one more electron. That's boron. Then to carbon, we put one more proton and we put one more electron. So we are on the same shell, you're adding more electrons and you're adding more protons. So as we go from left to right, the size decreases. This is the biggest guy. I probably should use a completely neutral color. So this is big. This is a little bit smaller. This is a little bit smaller. This is even smaller. This is smaller. This is smaller. This is smaller. This is smaller. Okay. So as you go from left to right, the atomic size decreases and the concentration of the negative charge decreases. It's more jam-packed. It's like a little ball of electronic charge. It's like super powerful. Smaller is, large is not great here. Okay, bigger is not better. Okay, as the size decreases and the charge increases, electronegativity increases. Okay, electronegativity, I don't need the pen anymore. Electronegativity I don't know if it means anything. Electronegativity increases left to right. Okay, electronegativity decreases top to bottom. Why? Because you're adding another shell. You're adding another shell. Here to here, just shell 1, shell 2, then shell 3, then shell 4, then shell 5, then shell 6. As you're expanding the radius, the size increases. Size decreases this way, size increases this way. Okay. As you're adding one more shell, you go further away from the sun, further away from the nucleus, further away from the center, from the pit, in the middle of the atom. So you're increasing the size, you're spacing out the electrons, and the atoms, hunger for holding on to electrons decreases. So electronegativity decreases this way and increases to the right. And you need to remember a few electronegativity numbers. There is a scale. I'll mention it sometime. Maybe for the time being, let's just focus on hydrogen and carbon. Hydrogen's electronegativity is, it's some scale. It's a relative scale. Electronegativity of, let me just write down a few elements. Hydrogen is 2.1. Some books will say 2.0. It's okay. Remember 2.1. Carbon is 2.5. Okay. Nitrogen is 3.0. Oxygen is 3.5. Fluorine is 4.0. This is the largest. 4.0 is the maximum of that. It's like 100 degrees centigrade. Okay, water cannot get hotter than that when it becomes steam. So that's the largest electronegativity number on in the periodic table. And these guys are very small. Lithium, I believe it's 0.9. Sodium is, or it could be 1, something like that. Boron is like 1 point something. I can't remember. I don't use boron so much. Okay. So you need to remember these numbers. Sooner you memorize it, better it is. But we're going to be using it, so it'll make more sense. So the bottom line is electronegativity of hydrogen is 2.1. Electronegativity of carbon is 2.5. Now we can actually appreciate the character of the different covalent bonds more than before. Okay. My clock has stopped working, 8:35. Okay, we are good. Okay. I think we are making decent progress today for a change. Okay, so when you look at this molecule, okay, look at this carbocation. This is a carbocation that has 3 hydrogens. This is a carbocation. Stay focused here in the center. This is the important part. That's the happening place. Stay focused here on this carbon. That's the central carbon. That's the central part of the carbocation. That's important. Okay, this is important. All right. So what does the central carbon have? Where the carbocation is 3 hydrogens. Over here, 2 hydrogens and a methyl group, 1 hydrogen and 2 methyl groups, and 3 methyl groups. What are we trying to do, and why did we have the discussion about electronegativity? Well, we are trying to establish an understanding for which carbocation is better and which carbocation is not so good. Okay. Now, what does a methyl group do? I always use this example. I'll use the metaphor in a second. Okay. If you look at this bond, what we are trying to figure out right now is how are these methyl groups influencing that central carbon. So tell me something first. Tell me something. Let's establish some fundamental understanding. If I'm a carbocation, right? Let's say I have very little money. In real human society, it doesn't work this way. If I need money, I don't think the rich will give me money. Okay, that's not how it happens. It's funny because probably the poor will give me money because they appreciate my pain more than the rich, right? So it really doesn't correlate very well how electrons, how elements behave in the periodic table and how we behave in real society. Okay, rich don't give to poor necessarily. There are exceptions, but generally middle class or maybe not so poor will give more to poor. So it really doesn't. It's a bad metaphor. Okay, that's unfortunate truth. So imagine if in an utopic world, in a perfect world, if I need money, will I be more comfortable if I have some people around me who have more bank balance, like they can support me? Can they reduce my anxiety of not having food tomorrow morning on my dining table with my family? Or what would the carbocation like to have in the vicinity? Somebody who can push electrons toward itself, toward the center, or somebody who can pull away electron density? What would be a good scenario? What do you think? What's your gut feeling? What kind of groups will make the carbocation better? Electron pushing or electron withdrawing?
I'd guess push.
William? Not William, Michael. I don't know what's going on here. Anybody else? Is there a William in our group? There is a William. No, there is his last name William. Yeah. Tiana Williams. Okay, no distraction. I'm really focused today. I'm very proud of myself this morning. No, I haven't gotten distracted yet. So anybody else? Michael says that having electron pushing groups will make the carbocation feel good, who can dump money. I have nothing. I don't know what I'm going to eat for lunch. So if somebody can, share $5 with me, that'll be good, right? Somebody can push $5 toward me. So our electron pushing groups make the carbocation better, or electron withdrawing groups make the carbocation better? What do you guys think? Anybody else?
Pushing.
Sorry?
I say pushing too.
Pushing too? Okay, and this is Crystal with an I. Thank you, Crystal. Anybody else? One more answer.
I'd say pushing.
And this is Tim. Okay, thank you. Thank you all. Yes, so let's figure out what this methyl group is capable of doing. All right, let's use those numbers. Hydrogen is 2.1 electronegativity, and carbon's electronegativity is 2.5. If that's the case, which way will the electrons be kind of pulled toward in this region? In this direction. All the bonds, CH bonds, will be polarized toward carbon. Will be kind of more, the electron density will be more toward carbon and less toward hydrogen. That's what it means. So it's going to be pushed that way. This is a very critical concept in organic chemistry. A lot of times people forget about that, and that creates a lot of problems. This is some basic fundamental knowledge, and it can really help you steer through organic chemistry, even if you go to graduate school or do whatever you want. Okay, if you're trying to solve some major problem, this understanding is very, very important. So the CH bonds in each methyl group, it's kind of like, I use this example. Let's say I'm standing in front of a movie theater. I'm trying to buy tickets, and I have three triplets with me, three little girls. Let's say my grandchildren. I can't say they're my children, too old for that. Let's say there are three little girls. They're two twins. They're standing behind me. I'm the last person in the line. There's a person in front of me, and those little girls are like the hydrogens, and they're pushing me. Okay, they're pushing me because I'm more electronegative than them. That each of the girls is pushing my back, and that push is being felt. Sometimes I'm almost tripping because I'm watching something on my cell phone. I'm distracted, and I end up pushing the person who is in front of me. Okay, so this push gets transmitted here. There are two methyl groups. They get pushed and they get transmitted toward that carbocation center. Okay, none here. Now, I'm going to jump a few steps and see if you guys can pull it off. I think you know what I'm going to do. This is carbocation 1. This is carbocation 2. This is carbocation 3. And this is carbocation 4. I haven't told you the whole story. And those are the kind of stories that are more attractive. Like the author doesn't tell you everything. And in your mind, you're taking a shower break and you're thinking like, my God, what happened? What happened? I think this is what happened. Okay, so I want to keep it under a little suspension. I want to ask you, throw the ball in your court and see if you guys can tell me. Do some thinking. Don't give me a knee-jerk reaction. Think. Don't cheat. Don't look on the way. Okay, which carbocation is most stable, happiest, and which carbocation is least stable, unhappiest?
I would say 1 and 4 are the happiest, right?
Don't ask. You have to answer.
Okay, I said that 1 and 4 are both equally as happy. And then
No, let's do this. Let's compare between. Let's keep it outside. Let's keep 1 outside. 2, 3, and 4. Which one is the happiest?
4.
Anybody else? I want to hear from more. Between 2, 3, and 4, which one is the happiest?
I think it's 4.
Why? Can somebody articulate?
Because it has more towards the carbon.
It has 3 methyl groups pumping electron to the carbon, kind of making it pacifying the carbon for not having enough electron. There are only 2. There is only 1. This one has nothing. Hydrogen is like a control. It has nothing. So this is generally the worst. Okay. So this is the worst. Most unstable. And that's the best. Most stable, okay? Because it has no assistance from hydrogen. Hydrogen cannot really pump electrons because it's just one little 1s orbital. It doesn't do much good, okay? Hydrogen is not so well, hydrogen is electronegative, but by itself it has to feel the push from another bond. Then it can exert that electron density push. Okay, it's really not very helpful. So this actually doesn't happen. It's so bad that it almost doesn't happen. This type of carbocation. This type of carbocation, okay, when you have 2 hydrogens attached, they are called primary or 1 degree. When you have only 1 hydrogen attached, it's called secondary. 2 degree. And when you have 3 0 hydrogens attached, it's called tertiary or 3 degree. Okay, so 3 degree carbocation is more stable than secondary. That's more stable than primary, and more stable than this is called a methyl carbocation. Because it's a CH3 group. This is called methyl. Methyl carbocation, CH3. Okay, CH3 carbocation is the worst. Primary is pretty darn bad, very bad. Almost doesn't happen. This is okay. This is meh. This is awesome. I think what we need to do is need to take a picture. Then I'm going to erase the bottom part and then continue with our story. Okay. So give me a second. Sorry, I'm blocking the camera. This is pretty heavy duty concept, and you guys need to really be able to navigate through it. But so I'm going to give you guys, okay, why am I looking at the clock? 8:48. Take a look at the board for like a minute and make sure you understand. Make sure you understand that. More electronegative that way, less electronegative this way. So it's this way. More electronegative as you go up and to the right. The reasons we have already discussed. Then we discussed this effect, the methyl group's electron pushing effect, and therefore this is the worst carbocation, little better. Okay, awesome. Okay, then we are going to go back to that situation and analyze and go from there, like which carbocation is better. You can already see what's going on there. But I'm going to draw these two carbocations in one color. If we draw it in one color, it will probably make more sense. Okay, I'll keep my mouth shut for a few seconds. What do you guys think? So far, so good? The concept of electronegativity and this business, it's understood. Any questions, any confusion? Shall I take your no answer as a positive sign or not positive sign? What do you guys are feeling comfortable, right? Okay, well, I'm assuming that you guys got it. Okay, so what I'm going to do is I'm going to erase this discussion on electronegativity right now. Okay, let's do that. So we just kind of step back and try to go over this electronegativity business and electron pushing and electron pulling groups. And now we are going to go back and revisit this scenario, these guys, the two carbocations that can form from an unsymmetric double bond when it reacts with an acid. I'm going to erase everything from this side. Just open up the space a little bit more. Okay, so let's just redraw these two guys so that you can kind of compare it with what you have seen in the past. So let me just draw this molecule with just two colors, okay? And it'll probably be easier for you to see what's going on. Let's draw this guy. So that's the carbocation, right? That's the important part. That's the carbocation, that's the important part. I'm going to draw this molecule, focusing here. So this carbocation has a methyl group, right? That's a methyl group. It's just, no, that's not a methyl group. That's the important carbon. This is the important carbon here. Okay. I told you that a tertiary carbocation has no hydrogens attached. A secondary carbocation has one hydrogen attached. A primary carbocation, pretty bad, has two hydrogens attached, and a methyl carbocation has three hydrogens attached, right? So this carbocation, you know what? Let's just simplify it. So this is the alkyl group. This is a methyl group. That's also a methyl group. So treat any alkyl group like a methyl group, okay? They're always going to be electron pushing. So this is going to push electron density. This is going to push electron density. This is also going to push electron density. It doesn't matter if it is a methyl or an ethyl or propyl or butyl, they always push electron density. I'm just going to write it down. All alkyl groups push electron density. Okay. Methyl, ethyl, propyl, whatever. Okay. So this carbocation with two hydrogens attached and this carbocation with one hydrogen attached, how would you designate them based on methyl, primary, secondary, tertiary? So let's say this is 1 and this is 2. This is 2. It's like a eye test. This is 1. What do you see? 2 or 1? Now 1 or 2? Which one is primary or secondary or tertiary or methyl? Let's start with it.
One is primary, 2 is secondary.
Oh no, Michael. Anybody wants to correct him?
Or first degree, second degree.
I could be messing with Michael. We don't know. I have a
Okay.
So which one is which? Somebody else. What's this? Primary, secondary, tertiary, or methyl? What kind of
Primary.
carbocation is this?
Primary,
Sorry,
primary,
primary. Somebody else. One more person. Who is this? Anybody else? Is this primary, secondary, or tertiary? Michael has answered and Danielle has answered. Somebody else, one more person. You just learned it. 2 hydrogens attached to the carbocation center. What kind of carbocation is this? Hurry up.
Primary?
Okay, so this is primary. This is secondary. Which one is better? Which one is more stable?
Secondary, right?
Don't ask, answer. This is better. This is going to happen. It may be non-existence. Okay, so I'm going to say this is major and this is minor. Okay, from this and this, the Br minus is going to come and make the final deal. Br minus is going to come in the next step and make the final product. What does the final product look like? In this case, the final product will look like that. In this case, the final product is going to look like this. How would you name them? So this is going to be your major product, and this is going to be your minor product. Maybe non-existent, maybe 1% and 99%. Who knows? I don't know the numbers. I haven't done that reaction yet. Okay, so if that's the case, let's say my question might be, name the 2 final alkyl halides, major and minor. How would you name this guy? Help me name it. Anybody? What's the name of this molecule and what's the name of this molecule?
Well, they're both bromoethane, right?
Ethane? 1.
Or oh, bromo 3 is a propane? Or I can't remember now. I have to pull it up.
Somebody else. Michael needs a break. Somebody else. Michael, you're forbidden. What is this? Bromo what? Somebody else who hasn't spoken today. And that's definitely not me. Speak to me, please.
That second one is an isopropyl, isn't it?
Yeah, don't go there, Fernando. Yes, you can call it isopropyl bromide. That's very, very clever. That's going to be the trivial name. Let's call it bromo something. What is bromo what?
butane.
Butane. How many carbons does butane have? You guys better figure out how
Oh,
many How many carbons do these molecules have? How many carbons did we start with? We haven't added a carbon, then you would get Nobel Prize. If you can add a carbon from nowhere, that's definitely going to be a Nobel Prize. If we can go from 3 carbon to 4 carbon, then man, I'm going to be famous. So 1 carbon, a 2nd carbon, and a 3rd carbon. The same deal here. It's just the location is different. Location, location, location. It's the terminal attachment, it's the middle attachment. Okay, so bromo what? Come on, guys, we have covered alkanes long time ago.
Propane.
Thank you. And who is this? Danielle? This is
Somebody
bromo.
else said it too.
Okay, bromopropane and this is bromopropane too. So how can we distinguish between the two?
1 and 2.
1 and 2. Okay. If I ask you this question in the next quiz, you better deal with it. 1 bromopropane and 2 bromopropane. 1, 2, 3. Whatever, whichever way, it doesn't matter. 1, 2, 3. That's major and this is minor. Sounds good? So when you have an unsymmetric double bond, weird things can happen. And I expect you to figure out which carbocation is more stable based on alkyl group location. And going from there, this reaction, this particular reaction is called, because this is being attached as a H plus, and this is actually an electrophile. This is the smallest electrophile, And let me ask you a difficult question. It's really a difficult question, but I think you can answer. So the name of this particular reaction is called electrophilic. I'm going to leave that second word as a blank. Electrophilic something reaction of alkenes. And that blank can be 3 different words. The blank word can be, you choose from one, substitution. Second word is going to be addition. And the 3rd word is going to be elimination. 3 types of reactions. Okay. Substitution means you replace a hydrogen with a bromine, or replace a bromine with a, I don't know, a hydroxy group. That's what it means. Substitution means I'm replacing my right arm with a little hook, like those pirates in the old days, right? I'm replacing my ear with a special hearing device. Okay, I can be half man, half robot. Addition reaction means everybody in that house stays and you are inviting a paying guest. Okay, so there were 3 people in the household, dad, mom, and a son or daughter, and now they have someone else living in the garage. You know, $50 a month. That's a pretty good deal. I have seen a person in Berkeley, my friends, I'm getting distracted, but this is a good story you must hear. This is like a long time ago in the 90s. My friend was living in Berkeley in an apartment, 1-bedroom apartment with 3 people, because it's very expensive. And then I went to visit them, and it turned out in the middle of the night, somebody was walking around in the living room where I was sleeping on a sleeping bag and talking about me and India and the caste system. And he was laughing, and I was really scared. I thought I was having a nightmare. Next morning, when I woke up, I pretended that I didn't hear anything. I fell asleep again. I asked my friend, like, who was that? Like, was one of your roommates in the living room? He said, no, we rent the closet to a homeless guy. He gets some check from government, and he pays us $50 every month, $100 every month to sleep inside the closet. So he comes in, he has a key, comes in at like 1 o'clock in the night, walks into the apartment, opens the closet, you know, kind of makes room behind the clothes. He leans back against the whatever the wall. It's not a walk-in closet, it's a small closet, and he sleeps like half sitting inside. And he was the person who was making fun of me and my origin. Okay, that's a good story. I didn't make it up. It's a true story. Okay, substitution, addition, or elimination. So you have this molecule, you have H where it's reacting with, and this is the outcome. Did anything fall off? Was anything substituted, or everything is there? Like that guy and that guy, everything has been put together to make this final deal. Is this a substitution reaction? Is this an elimination reaction, or is this an addition reaction? What kind of reaction is this? Let's say this is answer A. Michael, you cannot answer. Somebody else. And D is none. None of the above. Somebody who has an answer today. Is this substitution, addition, elimination, or none? It's essentially this sort of reaction, right? This is what the molecule looked like, and it reacted with HBr, and this is what it looks like now. The double bond disappeared. What does it look like? Does it look like a substitution reaction, elimination reaction, like a body part fell off? Or does it look like an addition reaction, like everything is there, what was there before, and then it has added some stuff? What kind of reaction is this? Addition, substitution, or elimination? Somebody who hasn't spoken today. Come on. You're testing my patience. That's what your mother probably told you when you're a toddler. You're testing my patience, Joe. Come on, let's go to the shop. Let's buy a camel. We have a long way to go. We have to go across the desert to the nearest, what is that called? Nearest shopping center. It's called Mirage.
Bazaar.
Sorry?
Closest bazaar.
I'm not following your answer. Who is that?
Oh no, I was going along with your story. A bazaar is a
Oh, bazaar.
place
Oh,
to
I
shop.
thought you were answering.
Yeah.
That's what happens when I talk too much. Okay, okay. I was thinking, yeah. No, I'm not asking about that. Addition, elimination, or substitution.
I would go with addition.
Okay, Craig says addition. Anybody else? Yay or nay?
I agree.
You agree? Okay, I'm not going to. It's addition. So this reaction is called electrophilic addition reaction of an alkene. Okay, electrophilic addition reaction of an alkene. Why electrophile? Because this dude is electrophile. That's the first step. Okay. I'm going to show you guys. We still have like 6 minutes. I'm going to take a picture of the board. If you have any
Can you explain
questions-
the difference between minor and major really quick again?
Minor and major, because this is a bad carbocation. This is a good carbocation. So if you have two choices, if you can sit down comfortably on a chair, or if you have to kneel down, let's say you go inside some bizarre church of a bizarre religion, and you are supposed to pray either sitting down on a chair or kneeling down on the carpet, and your knees are hurting from 10-mile walk that it took you to get there, right? So you can sit down on a chair. That's your major conformation, you're more comfortable to do that. Or you can kneel down and make yourself really uncomfortable and hurt your knees, right? Which conformation or which position you will be found in the church for, if you're there for like an hour, probably 50 minutes you'll be sitting on the chair, and maybe for 10 minutes you'll be sitting, kneeling down on your knees, right? So if this is bad, then this is not going to happen. That means the percentage of this product is going to be significantly less. Therefore, the bad carbocation leads to the minor product, and the good carbocation leads to the major product. That's the connection. Make sense, Craig and everybody else?
Yeah, I got it now. And you said something like the major would be like something like, let's say 99%
Something like
in
that.
the universe, whereas the minor would be like 1%, or but that could vary.
That ratio will vary depending upon how bad this is and how good this is. If it is tertiary and and primary, maybe 99 and 1. If it is secondary and tertiary, then maybe 60-40, who knows, 70-30. It depends on the situation. Other factors will play a role too. It's just going to be less than 50%, more than 50%. That's what will make it major and minor. Okay, I would not throw any numbers there, percentage wise. It's very qualitative at this point. Anybody else? Are we good? I think I took a picture. So let's erase the board. This is probably one of the two different mechanisms I'm going to teach this course. And I don't think it's going to be, I'm going to teach you guys any more mechanism other than one more, okay? Let's quickly talk about a couple more reactions. Pretty cool reactions. And one reaction is very commercially relevant, okay? You have heard the word, and I don't want to, again, get distracted. I'm very tempted to get distracted, but I'll try to control myself. Okay. How much time do we have? We have 3 minutes. Okay, let's see if we can pull it up. I'm going to show you a couple more reactions very quickly. So if you're starting from this reaction, let's do like a wheel reaction. And if we react it with, I'm going to use one color, HX, okay? We will form two products. How do we draw the products? If it is a dissymmetric molecule, 2 products. If it is a symmetric molecule, 1 product, because left and right doesn't make any difference. Okay. What will happen here? Well, I will add the hydrogen here, and you add the halogen here, or reverse. Add the hydrogen here and add the X here. This is going to be major, and this is going to be minor. What we just learned. And we learned the mechanism. Can we add water across the double bond? Yes, we can add water across the double bond. I'm going to use different colors for different reactions. Let's use green. We can add water across the double bond. How does water look like? Well, water looks like this. Can you just put the alkene in water and stir it up and you get a product out of it? It's not that simple. You need to activate the double bond using some proton. You need to use just a little bit of proton, okay, in the form of HCl. Just a little bit, so it doesn't overpower the whole reaction. Like this is catalytic. Just a pinch, maybe a drop. Literally a drop will do. What will happen from this reaction? Well, it'll again form 2 products. Okay. The proton will be picked up in one corner. You just memorize this reaction. I don't want to go through the mechanism. And OH will be added to the other end. essentially, if I draw it in one color, drop all the colors, this is basically this alcohol, and this is basically this alcohol. Okay, so you can add water across a double bond too. This is a pretty cool reaction. The next reaction is very interesting. Again, I'm not going to teach you the mechanism. If you take a double bond and if you react it with hydrogen gas with a metal catalyst, just stay for 1 or 2 more minutes. On Thursday, I'll let you guys go a little early. I'm not promising. Okay, a platinum or palladium catalyst or nickel. If you come back to 128A, I can tell you all about this reaction, how it happens. What happens to this double bond? Well, the double bond becomes single bond. Okay. The hydrogen is added. You are basically moving it back to the previous generation. So essentially, from alkene, from propene, you make propane. In one color, it's just this. This is one propene, or propene, that's propane. This reaction is called, you have heard this word, I guarantee you, hydrogenation. This is called hydrogenation. Hydrogenated fat and saturated fat and unsaturated fat, everything has to do with this reaction. One last reaction I'm going to teach you today. If you take this guy and react it with, usually we use bromine gas dissolved in something. Okay, it's actually a gas. What happens? Well, kind of like hydrogenation, the double bond disappears and the bromine is added across the double bond. Okay, this reaction is called bromination. Simple. I do not expect you to know the mechanisms, but I want you to figure out like what will happen if these reactions are done. So this is electrophilic addition reaction of an alkene. This is also electrophilic addition reaction of an alkene. This is called hydrogenation. This is called bromination. You should be able to pull off these reactions. On Thursday, we're going to do a few examples and then talk about alkenes. I definitely do not want to talk about alkenes after this week. Okay, so that's pretty much it. Have a good day, guys, and I'm going to take a snapshot of the board, and sorry I took a little extra time. Okay,
Thank you.
go. No problem. Have a good day and see you in less than 2 days. Bye. I'll make the video and everything else available as soon as I can. Okay. Bye, guys. Take care. Have a good day.